Hi everyone. In this video, we're going to talk through some of the model shrinkage and selection slides where we left off last Thursday. And so, in general, the idea here is that we're doing regular linear regression, or we now have multiple predictor variables. So more than one predictor variable, one response, and we want to assess whether or not it seems like, or rather, not, we want to assess which variables should be in the data set. And we're going to look at different ways we can go about such a thing. Now, in general, I'm going to give you the advice that you should never rely purely on a computer and algorithm in general to make a model selection choice. They can help you to do such things, but the methods that are used here are not like set in stone great methods. Many people believe these are terrible methods, and myself sort of included. These aren't going to be the greatest, but they are out there and they are widely used, and so that's why I'm teaching you them. Not necessarily an endorsement of them, but nonetheless, we'll get there. And so to check these methods out, I created some synthetic data here. So one response variable, which is y, and then I made 10 predictor variables. You've seen this before. 10 predictor variables. Some of them, if you look at the bottom, you can see how y is created. So it's created using x2, sort of x3, x7, and x10. And I just made these random because I was sort of bored, and I made them so that some of them were some of them had more influence than the others, and they all necessarily aren't linearly. So, like if you look at x3, there's some sign of some multiple of pi there, and so it's sort of circular in some way how x3 is behaving. And so I did that to give us a variety of things of how the data is made, but nonetheless, some of them, x2, x3, x7, and x10, were taken into account when making y, and some of them weren't. And so the question is, if I put all 10 in the model, is there a way that I can assess which ones are important or not? And one way is to just fit the model, fit a linear regression with all of them, look at the p-values, and take out the ones that aren't significant. And that is definitely a strategy, but it is a bad one for a couple of reasons. And I won't get into it so much, but we saw before how models work in tandem, and small changes can make, including some variables, can make coefficients significant. Some can make them not significant. And also, we shouldn't necessarily trust p-values like the word of God, so to speak. And so all of that leads me to other ways other than just fitting the data and looking at p-values based on the fit that has everything in the model. And so where we get is subset selection, or that's what we're going to start with first. And so we did go over best subset selection before, which is it fits all possible models, starting from the null model, which is using the mean of y to predict y, so using no predictors, all the way up to using all of the predictors and sort of everything in between. Okay, which is great because it gives you all possible combinations, but also can be terrible because it's going to be a lot of fits. It's going to be a lot of different models to fit. In fact, 2 to the p models. So for my situation, which we had just a slide ago, the data, if we fit with all 10 predictors, that's 2 to the 10th models, which is not a small number. Okay, and then the second thing we talked about, again, this is a review, is how do we make a determination about which of those models is better. Now we're starting to get into these apples to apples comparisons in which we can look at before, say with mean square error or residual standard error. So there are a bunch of them. So we saw residual standard error before, and I told you that was not that was sort of data specific because it matters how big your data is, how large the values are. It's not scale invariant, is what you would call it. Whereas something like r squared is scale invariant because r squared, the smallest is 0, the highest is 1. And so you can only use something like residual standard error if you're making apples to apples comparisons. And we are here if you're using the same data set. But there are lots of evaluation criterion out there. I'm going to show you, I show you 4 here, but this is just the tip of the icebergs. Akayake's information criterion, which is the top, and you see it is the residual sum of squares, which is what we used when we were talking about regular linear regression. We wanted to minimize the residual sum of squares, or rather the solution, excuse me, are the slopes and intercept that minimize the residual sum of squares. Excuse me. And all of these are variations on it. So first one is Akayake's information criterion. It's one of the older ones, and for some people think it's good, some people think it's bad. It's good and it's bad in different situations. So none of these are the sort of best always. They all have different things that they try, the different things that they're good for and different things that they're not so good for. But Akayake's information criterion, they found some problems with it, and so they created a corrected version. So sometimes you'll see AICC, which is the corrected version. There's also BIC there, Mallows C, and adjusted. And you can see the difference basically in the formulation there. They're not big, they're small differences, but they sort of matter in different situations. So anyway, how do we do this best subset selection? There's a package called OLSRR. I did show you this at the end, so we're finally getting to the place which isn't a review. But I fit all of them. Again, that's a lot, 2 to the 10th, which you could calculate is not necessarily a small number. So there are a lot of them. Okay, and so what I did is I took the output, I made it a tibble. I arranged it by lowest AIC. So lower AIC is better. Right? Lower AIC is better, as we see here. And for most of the evaluation criterion, lower is better, but AIC lower is better. Okay, and here's the top 15. Okay, and so if you look at the AIC, the best one has an AIC of 2004 point something. If you look at the adjusted, so things like the R squared and adjusted R squared, they are extremely close. Predicted R squared, which is next to it, so these are all different things, right? Mallows CP, AIC, there's the BIC, the S in front of it is for a person named Schwarz, where it comes from. There's all kinds of things there. Some of them are fairly close, some of them are not. Like there seems like there's a decent difference in Mallows CP there between, say, the first one and the 15th, whereas something like R squared or adjusted R squared, they're almost or are the same. And so the question is, when I look at these, and so you might be wondering, why have I highlighted the 15th one with a circle? And so you have to make a choice here. There's a trade-off between the best results and then how much you're putting into the model, how many how many predictors, we'll say, you're putting into the model. And so you can see the M index is which particular one that fit was. So the bottom one was the 56th model it fit. N is how many predictors are in the model. And then it says predictors, which ones were, all the other ones. You have to make a choice about this trade-off between having the least number of predictors and then the best results. So, and so I give you a piece of advice down at the bottom. When choosing between models that had similar diagnostics, and I would argue that most of these are very similar, you want to choose the model that has the least number of predictors. This, as a term, is called model parsimony. Parsimony. So you want a parsimonious model, which is a model that includes the least number of predictors that get you the best response. And so if I were looking at these models, you see that 56 down there has the least number of models, at least number of predictors, 3, and has similar results. And so that might be advantageous to pick that one. You could also look up and see the second best AIC has 4 in it, which is better than all the ones around it. So you might also want to pick that one. Again, there's no right answer. There's no magic bullet. There's no magical answer that will be right all the time. But model parsimony is something that you should always keep in the back of your mind as which one you should choose or what kind of model you should make. So now, it's probably infeasible. So to do the best subset regression, which is what we just did, when there are many predictors. It didn't take, if you run the code that I give you for best subset selection, depending on your, if you're running it online, on your personal computer, and what type of computational power you have, it's probably going to take between 1 and 3 seconds, maybe 4 seconds to run. But when you increase the number of predictors, so and just start doing calculations like 2 to the 10th, 2 to the 11th, 2 to the 12th, 2 to the 20th, 2 to the 50th, so on and so forth, it starts to get crazy. For instance, if you think back to the Ames Iowa housing data set, or Ames housing data set that we had before, there were 81 predictors in there, and so that would be 2 to the 81st number of possible models, which is way too many. So there are different methods that don't do all possible subsets that still get at this idea of choosing the best subsets out there, like a subset of all of them. And they are 3 of them are popular: forward, backward, and stepwise. These especially have gotten a lot of criticism, and rightfully so, over the past. These are ones that I would not necessarily endorse, but are used, and so you should at least know about them. And they may be used, or you may want to use them to inform your choices about what you use. So anyway, let's get to the models. Okay. And so if you read the descriptions here, a forward starts with a model with no predictors, that null model, and then adds a variable one at a time until some stopping criterion is met. Basically meaning whatever criterion you use, AIC, BIC, there are different like p-value approaches. You don't see a significant decrease in AIC or increase in R squared. And so we have some sort of cutoff, and when that cutoff is hit, it stops. Backwards takes the backward approach, which is you start with all the predictors and you take out a predictor one by one, again, based on some criteria, and then you stop when you stop making noticeable increases or decreases in your criterion. And then stepwise is a combination of both that can both add and subtract predictors. So what does that look like? Here's forward, and so it'll show you which variables it added. So you can see in the output here, it added 2, then 3, then 7, then 4, then 10. Okay, and so you can see, based on something like adjusted R squared, or really all of the values, you see AIC decreasing by a lot when you, in the first couple, so 2690 down to 2390, down to 2006, 2004, and then added 2010. Now you get much smaller stuff, and so the guess would be also adjusted R squared. You're just barely making headway, and so you might guess the next one that would be added after X10 probably might make R squared go down, might make AIC go back up. So bad sort of things happening. Backwards, here they show you what are taken out. So it takes out X9, then and X1, X6, 5, 6, and 8. Okay. So again, it's coming to the same conclusion, which may not always happen. It is coming to the same conclusion. Here, because I've made some fake data, and so it's sort of easy to tease out the relationship. Also, it seems to be making roughly the right choices. So the 4 that were actually involved in the model were X2, X3, I think X7 and X10. Let's go back and look. X2, X3, X7, and X10. So it seems to be getting that. And then X4 somehow, even though it's not there, somehow made it into the model. It looks good. And so here is stepwise. So you notice OLS step. This was forward. This is backward. This is both. Okay. Now here the additions make more sense than the subtraction. So it tells you what method it is over here on the left, and various things. So this looks the same as a forward selection, but it could, in theory, put a variable into the model and then later take it out based on certain criterion. Okay. So that's where we're going to stop this video, and we'll come back in the next video and talk about shrinkage and penalization methods.